Hi everyone, and welcome to the MCAT A series of lectures in physics. In today's lecture we are going to be covering translational motion. In particular, I will go over some common units that are used in physics, some of which you may have met before, for example the kilogram and the second, and others that may be new to you. I will then introduce the concept of vectors and describe why and how they are useful in physics. I will then introduce some mathematical tools associated with vectors that are useful in the problems that come up in the MCAT. Then I shall discuss some various common vector types that come up quite often in physics, for example, velocity and acceleration. I will then use this concept of vectors to describe actual real-world motion of objects and particles, both in linear motion and in projectile motion. I will then finish this section by having a brief introduction to circular motion. In both physics and mathematics, numbers are meaningless by themselves. If I say, for example, something is 7, well, that doesn't mean anything unless I say 7 seconds or 7 kilograms or something. I need to have some unit afterwards so that we know what we are talking about. In America, we use what's called the imperial system, sometimes also known as the FPS system, F being foot, P being pound, and S being second. However, on the MCAT, you rarely see feet, pounds, or seconds. Instead, the MCAT typically uses the metric system, which is used almost everywhere else besides America. The metric system is also known as the MKS system for meter, kilogram, and second, or sometimes you can also see CGS, centimeter, gram, second. In total, there are 7 what is known as base units. These are known as base units as all other units are a function of these units, as we shall see shortly. There is the meter, which is the unit of length and has a symbol m. And you'll also see things like the centimeter, which is 1/100th of a meter. You'll also see a millimeter, a kilometer, and so on. There is the kilogram, which is the unit of mass and has a symbol kg. And again, you'll see things like gram and milligram and so on. There is the second, which is the unit of time, which is also used in America in the imperial system. And it has a symbol of S. And again, you'll have minutes, hours, days, years, centuries, etc. There is current, which has to do with the flow of charge, and we will talk a lot about this in a future video. It has units of ampere and a symbol of A. There is Kelvin, which you may not have heard before. You may be more used to Fahrenheit. That is the unit of temperature and has a symbol capital K. Then we want to quantify the amount of a substance, how much of a substance we have, how much we are dealing with. To do that, we use the unit of mole, which has a symbol MOL. And finally, this one doesn't come up on the MCAT too often, if at all, but just so you are aware of it, there is the candela. That is the unit of luminous intensity, which has to do with brightness and photons and light, which we will discuss, but we won't discuss this unit in particular. It has a symbol of CD. All other units are known as derived units, as they are derived from these base units. For example, there is the Newton, which is the unit of force and has a symbol of capital N, and that is equal to or equivalent to kilogram meter squared per second to the power of 4. There is also the joule, which is equivalent to kilogram meter squared per second squared. The reason why we have the Newton and the joule is so that we don't have to always write down these complicated functions of these base units. It's to make our lives simpler. Nothing more, nothing less. Finally, I've already discussed some prefixes that come with units. For example, the centi, which is 1/100th of a something, a milli, which is 1,000th of a something, kilo, which is 1,000 times something, and so on. There are also 2 prefixes which you may not have heard of before, but which you do need to know for the MCAT. One of them is known as the angstrom and has a unit A with a little circle on top. That is equivalent to 1 × 10 to the minus 10 meters. And it is used often when dealing with things on the atomic scale. Speaking of the atomic scale, when we are interested in energies at that scale, we typically don't use joules because 1 joule is too big. We instead use what is known as the electron volt, which has a symbol small e capital V, and it is approximately 1.6 × 10 to the minus 19 joules. This is equivalent to the amount of energy gained or lost by an electron moving through an electric potential of 1 volt. What this means will become clearer in future lectures. Quantities are split into two different categories, one of which is scalars. Scalars are quantities that have magnitude but no direction. For example, we can talk about traveling a distance of 5 meters. We have not given that quantity a direction, and therefore it is considered a scalar. We can also say that a car is going, for example, 80 miles per hour. Again, no direction, it is a scalar. We can say something has a certain amount of energy, and again, there is not a direction associated with that, and that is again a scalar. Something that is incorrectly described as a scalar in the real world is weight. We typically say that we weigh 200 pounds or something like that. However, that is incorrect. What is in fact correct is to say that an object's mass is 200 pounds or 80 kilograms or whatever it may be. Mass is the scalar. And a final example of a scalar is temperature. We can say that it's 90 degrees Fahrenheit outside, and again, that does not have a direction. Vectors, on the other hand, have both magnitude and direction. For example, if we apply a force to something, we have to apply that force in a certain direction, either by pushing it or pulling it, and so on. Displacement is the vector equivalent of distance. When we say that we have gone 20 meters west, for example, that is no longer a distance, it is now a displacement. Similarly, velocity is the vector equivalent of speed. We can say that our car is going 40 miles per hour northwest, it becomes a vector. Finally, as I mentioned earlier, weight is in fact a vector and is actually a force, an example of a force. It is the gravitational force that is attracting us to the ground, more precisely to the center of the earth, and we will discuss this further in a later video. To visualize a vector, we usually represent them by arrows. The length of the arrow tells you the magnitude of the vector, and its direction naturally tells you the direction of the vector. Whatever the name of the arrow is, for example A, we usually put an arrow on top of it so that we remember it is a vector. Just to pre-warn you that physicists tend to be very sloppy and leave out this arrow when writing it down. So if you don't see an arrow on a vector and you expect it, don't worry, you are probably correct. If we are only interested in the magnitude of a vector, the way we write that down is by writing down the vector name with the arrow on top and then putting two lines, one to the left and one to the right. That means the magnitude of vector A. One thing we would like to do with vectors is to add them together. For example, if we have multiple forces acting on an object, it would be useful to know what the net force on that object is. When adding vectors together, the sum of these vectors is known as the resultant vector. There are multiple ways of adding vectors together, two of which you must know for the MCAT. The first method is known as the tip-to-tail method. For example, if we have vector A and vector B, then we are free to move these vectors about as long as we don't change their orientation. To add them, we can move vector B such that the tip of vector B is on the tail of vector A. The resultant, which I shall call C, is then equal to the vector that goes from the tip of vector A to the head of vector B. This method is very useful when we are simply trying to draw vector C. However, it does not give us a lot of information about the length or the angle that vector C is at. One advantage of this method is that it allows us to add multiple vectors easily. For example, if we wanted to add 3 vectors, we could place the third vector at the head of vector B, and then the resultant of the 3 vectors would go from the tip of vector A to the head of this new third vector. The main caveat of this method, however, is that it does not give us any information about the length or the angle of this resultant vector. We get the visualization of it, but we don't get actual numbers from it. The more common method to add vectors is by what is known as decomposing the vectors, finding what are known as their components. Decomposing is in fact going backwards in the tip-to-tail method. To see this, let us just look at one vector, vector A. Just like in the tip-to-tail method, this vector A is equal to this vector A sub x plus this vector A sub y. As you can see, I've gone a bit backwards. What is the benefits of this? If this vector A is at the angle theta as shown, then we know from trigonometry that cosine of theta is equal to a sub x over a. And therefore, this new vector a sub x is equal to a cosine theta. Similarly, a sub y is equal to a sine of theta. That is vector A decomposed. I have written vector A as the sum of a horizontal vector plus a vertical vector. For example, if the magnitude of A is 10 and it is at an angle of 30 degrees to the horizontal, then A sub x is equal to 10 cosine 30, which is equal to 5 root 3, as cosine 30 is root 3 over 2. This may seem counterintuitive, as it seems like we've gone backwards. We had one vector and now we have two vectors. Why is that useful in adding vectors? Well, if I had another vector b, I could do the same thing and find a b sub x and a b sub y. And then I could simply add the horizontal bits together, the horizontal components, a sub x and b sub x. That will give me the horizontal component of the resultant vector c sub x. Similarly, I could do the same with the vertical components a sub y and b sub y to get c sub y. Using these two vectors, I could now reconstruct C. However, I now also have information about the length and direction of C. This is because if we look at vector A again, then tan of theta is equal to opposite over adjacent. Tan of theta is equal to a sub y over a sub x. And therefore theta is equal to the tan inverse of a sub y over a sub x. Similarly, when we have c sub x and c sub y, the resultant components, we can also find the angle of this resultant vector. Using the same method, it will be tan inverse c sub y over c sub x. So we actually know the actual angle of the resultant vector. How do we find the length? Well, by Pythagoras' theorem, if we again look at vector A, we know that the adjacent squared plus the opposite squared is equal to the hypotenuse squared. In other words, a sub x squared plus a sub y squared is equal to a squared. We could also apply this method to C to say that c squared is equal to c sub x squared plus c sub y squared. In other words, c is equal to the square root of c sub x squared plus c sub y squared. Because we know c sub x and c sub y, we can also work out the length of the vector c. If we wanted to add multiple vectors using this component method, we would find the horizontal components of each vector, a sub x, b sub x, c sub x, d sub x, and so on. Similarly, for the vertical components, we would then add up all the horizontal components to get our resultant x component, and add up all our vertical components to get our resultant y component. If we instead wanted to subtract two vectors, for example, if we wanted to work out b minus a, what we would do is first flip a. Flipping a turns a into minus a. We would then add b to minus a to get b minus a. Now that we have talked about adding vectors together, we can now talk about vector multiplication. Now we already know how to multiply a scalar by a scalar. That is just everyday normal multiplication. 7 times 6 equals 42, for example. However, a vector multiplied by a scalar and a vector multiplied by a vector is something slightly different. Both of those things are something that we have to know for the MCAT. For example, in a future lecture, we will find out that force is equal to mass times acceleration. Mass times acceleration is a scalar multiplied by a vector. We need to know how to do that for the MCAT. Similarly, work, which we will define in a later lecture, is equal to force multiplied by displacement. That is a vector multiplied by a vector, and therefore we also need to know how to do that for the MCAT. To begin, let us look at a scalar multiplied by a vector. A scalar multiplied by a vector simply changes the magnitude of that vector. It does not change its orientation. It does not change the direction of that vector. For example, if we have a vector A, like this one here, and we multiply that vector by the scalar 2, all that does is doubles the length of that arrow. For example, if it was a force, we multiplied that force by the scalar number 2, that would increase that force by a factor of 2. One final thing to note is that when I say it cannot change the orientation, it can cause the arrow to flip. For example, if I instead multiply this vector by the scalar -2, it would double the length of the arrow, but it would also cause the arrow to flip. For a vector multiplied by a vector, there is two different possibilities. The first of these is known as the dot product. Let's consider the dot product of two vectors a, b. The way we say this is a dot b, and that is equal to the magnitude of a multiplied by the magnitude of b, just scalar multiplication here. Remember, magnitude of a vector is simply a scalar, so we have a scalar by a scalar, multiplied by cosine of theta, where theta is the angle between a and b. The dot product of two vectors always results in a scalar. As you can see here, we have magnitude multiplied by magnitude multiplied by an angle. We end up with a scalar, three scalars multiplied by each other. Anytime you multiply vectors together and expect to get a scalar, you always do the dot product. As I mentioned earlier, work, which is a scalar as we will see in a future video, is equal to the dot product of two vectors. If we instead expect to get a vector back when multiplying two vectors, we do what's known as the cross product. If we have two vectors a and b, then the cross product of these two vectors is known as a cross b. A cross b is equal to the magnitude of a multiplied by the magnitude of b multiplied by sine of theta, where theta is again the angle between a and b. Something you should immediately note here is again we have a scalar. Magnitude of a multiplied by magnitude of b multiplied by sine of an angle. Those three numbers multiplied together give you a scalar. But I have just said that we get a vector. We have a magnitude. How do we get the direction of a cross b? To work out the direction of a cross b, we use what is known as the right-hand rule. To demonstrate this, allow me to draw a diagram. As you will quickly find out in this series of videos, art is not my strong point, so I hope you can understand what I'm doing here. But we have a right hand. If we take our right hand and our two vectors a and b, if we put vector a in the direction of our thumb, okay, so imagine your hand is outstretched as it is kind of sort of here, and take our thumb and lie vector a along our thumb, then take vector b and lie it along the palm of our hand, so along the direction of our fingers, then the direction of a cross b is equal to a vector that points out of your palm, a vector that is at right angles to your palm in that third dimension, okay? If that's hard to visualize, right now take your right hand and put it in front of your face. Have your thumb pointing up and your fingers pointing to the left, okay? So your thumb pointing up, that's the direction of vector A. Your fingers pointing to the left, that's the direction of vector B. And the direction of vector A cross B is the vector that is pointing out of your palm towards your face. If you are still struggling to visualize that, I would recommend having a quick look online at images of the right-hand rule. Now that we know the mathematics we need to use vectors in the MCAT, let us now discuss the most common vector types that come up in the MCAT, starting with what is known as displacement. Displacement, if you like, is the vector equivalent of distance. Besides the fact that direction is important in displacement and not in distance, there is also one more important feature of displacement that you need to be made aware of. If we consider a person going from point A to point B and following a complicated messy curve as shown here, then the distance that person has gone is equal to the complicated length of that curve. The displacement, on the other hand, is simply equal to the length of the straight line joining A to B. The distance, as I'm sure you've seen before, we represent using the letter small d. To distinguish displacement from distance, we instead use small s, with of course our arrow on top to let us know it's a vector. To take a more extreme example, let us consider an athlete running a lap of a running track. A typical running track is of length 400 meters. So once that athlete has run one lap, he or she has run a total distance of 400 meters. However, her displacement is 0 meters because she is back to where she began. Points A and B in the example above are now overlapping. Points A and B are at the same point. Therefore, their starting point is at the same point as their end point. In that case, the displacement is 0. Similarly, velocity can be considered the vector equivalent of speed. Speed, as I'm sure most of you are aware of, is equal to the distance per unit time. When we talk about something going at 50 kilometers per hour, that is kilometers per hour, distance per time. Similarly, velocity is displacement per time. As with displacement and distance, which had the same unit of meter, velocity and speed also have the same unit, which typically on the MCAT will be in meters per second. There are two different forms of both velocity and speed that you need to be aware of. The instantaneous speed is equivalent to the magnitude of the instantaneous velocity, which is a measure of the average velocity as that change in time approaches zero. In other words, the instantaneous velocity is equal to the limit as the change in time goes to zero of the total displacement over total time. It is the velocity at a particular instant in time. The average speed, on the other hand, is not necessarily the same as the average velocity. This is because average speed accounts for actual distance traveled. Average velocity does not. Average velocity is equal to the change in displacement or the total displacement over the change in time or the total time. Average speed, on the other hand, is equal to total distance over total time. If we again look at our athlete running a lap of a track, then the average speed in that case would be equal to the total distance divided by the total time. The total distance of a typical running track is 400 meters. And let's assume that our athlete ran that race in a very quick time of 40 seconds. The average speed would then be 400 meters over 40 seconds, which is 10 meters per second. The athlete's average velocity, on the other hand, will be zero, because their total displacement is zero. Their starting point is the same point as their end point. Their total displacement is zero, therefore we have 0 over 40, which is 0 meters per second. So remember, instantaneous speed is the same thing as the magnitude of instantaneous velocity, but average speed and the magnitude of average velocity are not necessarily the same and typically are not in the MCAT. Speaking of velocity, if we wish to change the velocity of an object, we need to apply a force. There are many types of forces that we need to know and be aware of for the MCAT. A common force that we know very well is a push or a pull force. For example, we can imagine pushing an object with our hands or pulling it with a rope, and we shall see examples of doing this in a later video. Another well-known force is that of gravity. Gravity is the attractive force that keeps our bodies on the ground. Not only this, but it is also the force that keeps the Earth and the other planets orbiting the Sun. There are also other types of forces that you need to know for the MCAT, for example, the electrostatic force, which we shall discuss in more detail in future videos. The unit of force is the Newton and has symbol capital N. And as I said earlier, this is a derived unit. It is not a base unit. It is composed of base units. The Newton is equivalent to a kilogram meter per second squared. At this point, I would like to mention that in the MCAT, you should assume that the acceleration due to gravity is 10 meters per second squared unless it is otherwise stated. This is the acceleration of any object falling due to Earth's gravitational pull. The more precise number of 9.8 or 9.81 can sometimes be stated on the MCAT, but if it is not, you should assume that it is 10. This number means that any object, irregardless of its mass, falls at the same acceleration. This does not take into account air drag, for example, which would slow an object down. This is only the ideal situation. The gravitational force acts on a small object and a big object. For example, gravity keeps us on the ground because gravity is attracting me to the center of the Earth. As I also said, gravity can also act between two large objects, for example, the Earth and the Sun. In general, however, gravity acts between all objects as long as those objects have mass. If we consider a mass m1 and a mass m2, which are initially separated by a distance r, then the gravitational force is given by this equation. F is equal to capital G, which is a constant, m1 multiplied by m2 divided by r squared. Where this capital G is known as the universal gravitational constant, it is approximately 6.67 times 10 to the minus 11 Newton meter squared over kilogram squared. The fact that this is such a small number means that the gravitational force will be small unless M1 or M2 is really large or is really small, the distance between them. This is why, for example, if you have one cup placed next to a second cup, they are not immediately attracted towards each other due to gravity. You need to have at least one very large mass for the gravitational force to be noticeable. One final point to note on gravity is that it is always an attractive force. You can never have two masses repelled due to gravity. They are always attracted towards each other. There are examples of forces where this is not always the case, for example the electrostatic force, which we will discuss later. Continuing on with this idea of a gravitational force, let us now discuss weight. As I mentioned earlier, mass and weight are often confused in the real world. When we say that something weighs 200 kilograms or 200 pounds, that is in fact an incorrect statement to make. Instead, we should be saying that the mass of that object is 200 pounds or 200 kilograms. Weight is instead an example of a force. As a force, it therefore has units of Newton and not kilogram or pounds. Mass is said to be an intrinsic property of an object. It does not depend on the environment that that object is in. Weight, on the other hand, is dependent on the environment and is known as an extrinsic property. Your mass on the Earth is the same as your mass on the Moon. It is your weight that is different on the Earth and the Moon. Your weight on the Earth is about 6 times greater than your weight on the Moon. The relationship between weight and mass is given as follows. Weight is equal to mass times the acceleration due to gravity, this small g that I mentioned earlier. And I should have in fact had an arrow on this small g earlier, because, as I shall discuss in a second, acceleration is in fact a vector. Gravity is accelerating us towards the center of the Earth, so this small g points towards the center of the Earth. As it has a direction, it is a vector. For example, on Earth, if an object's mass is 60 kilograms, that object's weight is 60 by 10 or 600 newtons approximately. On the Moon, on the other hand, the object would still have a mass of 60 kilograms, but its weight would be about a sixth of that on Earth's, so it would be about 100 newtons. Finally, I have already mentioned acceleration when it comes to gravity. However, I have not defined what acceleration actually is. Acceleration, as you may have guessed, is the rate of change of velocity per unit time, just as velocity is the rate of change of displacement per unit time. As it is a rate of change of velocity per unit time, it has units of velocity per time, meters per second, or meters per second squared. Acceleration is a vector, but unlike velocity, it does not have a scalar equivalent. There is only acceleration. However, similarly to velocity, we can also talk about the instantaneous and the average acceleration. Average acceleration is defined as the change in velocity or the total velocity per total time or change in time. And, as I already mentioned, has units of meters per second squared. And similarly, instantaneous acceleration, or the acceleration at a particular moment in time, is the limit as the change in time goes to zero of the change in velocity over the change in time. Accelerations are in fact caused by forces, and we shall discuss this relationship in more detail in a future video. Now that I have introduced various vector types, I would like to now finally use these vectors to solve real-world problems, in particular with regards to motion. To begin, I will look at linear motion, that is, motion that is only in one dimension. For example, we could consider a car that's only moving north or south or east or west. Or we could consider a ball or an object that's thrown vertically up in the air rather than at an angle. For the case of a constant acceleration, that is, when the acceleration is not changing, this motion is fully described by what is known as the Suvat equations, which I have here. These equations describe the motion as follows. If an object has an initial velocity u, and then moves through a displacement s with an acceleration a, and a final velocity v after a time t, these equations describe that motion. Now, it may appear as if I pluck these equations out of thin air. However, they can actually be understood by what we already discussed. For example, I just defined acceleration as the change in velocity over the change in time. In other words, a is equal to the change in velocity, that is the final velocity minus the initial velocity, which is v minus u, divided by the change in time, which is simply t minus 0, because we are defining the initial velocity as being the velocity at time t is equal to 0. If we then rearrange that, we get v is equal to u plus at, which is the first equation of the Suvat equations. The other equations can be derived in a similar manner, and I recommend that you try it in your own time. Note that we have 5 variables in total. We have the initial and final velocities, the displacement, the acceleration, and the time. Each one of these 4 equations has 4 of those variables. Each equation is missing one variable. For example, the top equation, v is equal to u plus at, does not have the displacement in it. This is why we need 4 equations, because unfortunately there is no one equation that has all 5 variables in it. Therefore, typically on the MCAT, you would be given 3 of the quantities, and you would have to figure out which of these 4 equations you need to use to find the 4th quantity. For example, you could be given the initial velocity u, the time t, and the acceleration a, and asked to find the displacement. Because in that instance you don't care about the final velocity v, you would use the second equation, which is missing the final velocity. As mentioned, these equations could be applied to, for example, a vehicle moving horizontally, or they could be applied to an object being thrown in the air. In that case, the acceleration would be the acceleration due to gravity g, which I mentioned earlier, which for the MCAT you take as being 10 meters per second squared. Let's look at a simple example to make sure we understand how to use these Suvat equations. In this question, let's assume that we have an object that we are holding in our hands, and then we decide to let it go. Let's assume that we have the object initially 20 meters off the ground, and that we are looking for the time it takes for that object to hit the ground. Well, because we are just dropping the object, we are not forcing it towards the ground, the initial velocity will be 0 meters per second. The reason that this object is falling is because it is accelerating towards the ground due to gravity. Therefore, the acceleration will be 10 meters per second squared. As mentioned in the question itself, the displacement is 20 meters, and we are looking for the time. Note also that I have the acceleration and the displacement both being positive here. The reason both of these are positive is because I have randomly chosen the downwards direction to be positive. I could easily have also chosen the upwards direction to be positive, and then both of these would have been negative. However, to avoid negative signs, I've chosen the downwards direction to be positive. However, I would have gotten the same answer either way, and you should check that to be sure. I have chosen the downwards direction to be positive, and therefore, since acceleration acts towards the center of the Earth, the acceleration is positive. And because the object is going from a high height to a low height, its displacement is also positive because it is also acting in the downward direction. If I drew an arrow from its starting point to its end point, that arrow would point down, and its displacement is therefore down. Going back to this question, we know u, we know a, we know s, and we are looking for t. Therefore, we do not care about v, the final velocity. Therefore, we want to use the equation that does not have v in it, which is the second equation. The top, the third, and the fourth equations all have the velocity v. Hence, we use s is equal to ut plus a half at squared. Therefore, s, which is 20, equals ut, that's 0 multiplied by t, which is what we're looking for, plus a half a, the acceleration due to gravity, which is 10, multiplied by t squared. Therefore, 20 is equal to 0 plus a half 10t squared, or 20 is equal to 5t squared. Doing some rearranging, we get t squared is equal to 4, or t is equal to 2 seconds. That means it takes this object 2 seconds to fall the 20 meters. Now let us consider a more difficult scenario, that in 2 dimensions, known as projectile motion. When in 2 dimensions, our vectors represented by arrows can now be diagonal, not specifically horizontal or vertical. However, these SUVAT equations only work if these arrows are in the same direction or flipped in the same direction, for example, up or down. They do not work, for example, if we have an arrow that is horizontal and another arrow that is diagonal. They only work if the arrows are all in the same plane. To deal with this, let us think back to our idea of decomposing vectors. We can decompose vectors into horizontal and vertical components. Doing so, we can then apply our SUVAT equations in the horizontal direction and also apply SUVAT equations in the vertical direction. Therefore, in projectile motion, we now have more quantities we need to deal with. This is because we now have a vertical and horizontal component for each vector. We have s sub x, u sub x, and so on, and we also have s sub y and u sub y. T, remember, is a scalar. Time is a scalar. We don't say we go 5 seconds west or north, but everything else in the SUVAT equations is a vector, so they now have components. Therefore, we now have 9 different quantities in total. We have the horizontal and vertical components of displacement, initial velocity, final velocity, and acceleration, and we also have time. And also we now have 8 different equations because we now have those 4 SUVAT equations but in the horizontal and vertical directions. For example, v is equal to u plus at, and the horizontal direction becomes v sub x is equal to u sub x plus a sub xt, and similarly for the y direction. This may seem like a lot of equations, but don't worry, a lot of these equations simplify down in typical questions in the MCAT. For example, if the motion is under gravity, then we know that the acceleration due to gravity acts towards the center of the Earth. In other words, in these types of scenarios, the acceleration is purely vertical. That means that a sub x is equal to 0, and a sub y is equal to that small g is equal to 10 meters per second squared. Again, it is hard to visualize this without first doing an example, so let's do a very common example that comes up on the MCAT. Let us say we have something simple like a soccer ball that is sitting on the ground, and we decide to kick it at an angle. Let's say when kicking the soccer ball, we give it an initial velocity of 20 meters per second, and we kick it at an angle of 30 degrees to the horizontal. The question could be, what is the time it takes for this ball to reach its maximum height? As in the previous example, we need to define what directions we are considering positive. We now have 2 directions we need to worry about, up and down and left and right. So we could define up as positive and left as positive, or down as positive and left as positive, and so on and so forth. Whichever way we do it, we should always get the same answer. So I'm going to choose up as positive and right as positive, but in your own time, you should change that around. For example, you could put down as positive and right as positive, and you should get the same answer I'm going to get now. But just remember, before you start any motion question, you have to define which direction your vectors are positive. It doesn't change the answer, but you just have to be consistent throughout your question. So in this example, we have that u, the diagonal velocity vector, is 20 meters per second. As this is a gravitational question, we have that a sub x is 0 because gravity only acts vertically. And the acceleration due to gravity, a sub y, is equal to minus 10 meters per second squared. Minus, as I've defined the up direction as being positive. As gravity pulls objects towards the center of the Earth, in other words downwards, the acceleration is therefore negative. Great, I have the acceleration broken into its components a sub x and a sub y, but I don't have the initial velocity u broken into its components, so I have to do that first. Remember, a vector sub x is equal to that vector cosine of that angle to the horizontal. Therefore, u sub x is going to be equal to u cosine of the angle. In other words, u sub x is equal to 20 cosine 30. Cosine 30 is root 3 over 2, therefore 20 cosine 30 is 10 root 3 meters per second. Similarly, u sub y is 20 sine 30, sine of 30 is a half, therefore u sub y is 20 by a half, which is 10 meters per second. Is this all we know? Well, I hope not, because this is not enough information to answer the question. All we know so far are the accelerations and the initial velocities. Remember, each of our equations has 4 quantities in it. We only have 2 in each direction right now, a and u. Well, remember, the question is asking us what is the time it takes for the soccer ball to get to its maximum height. Is there something special about the maximum height? What is going on at the maximum height? Well, if we look at our velocity vector, which is changing, as the ball follows this curve, the velocity vector is changing. As you can see, it's becoming more horizontal. At the maximum height, the velocity vector is purely horizontal. It is purely in the x direction. That means that at its maximum height, its velocity in the y direction is 0. Therefore, as the ball at its maximum height is our final position in our question, we say that the final velocity in the y direction is 0. Now we have everything we need, because remember, we are looking for the time. Therefore, if we now look at our y components, we now know 3 components in the y direction. We know the acceleration in the y direction, we know the initial velocity in the y direction, and we also know the final velocity in the y direction. This means that we should now have enough information to find a 4th quantity, because remember, our Suvat equations have 4 quantities in it. If we know 3 quantities, we should be able to find a 4th. Which of our equations do we use? Well, we know A, U, and V, and we are looking for T, therefore we don't care about S, we don't care about the displacement. The equation that does not have the displacement in it is V is equal to U plus AT, which for the Y direction is V sub Y is equal to U sub Y plus A sub Y times T. Subbing in what we know, V sub Y is equal to 0, U sub Y is equal to 10, and A sub Y is equal to minus 10, we get 0 is equal to 10 minus 10t. In other words, 10t is equal to 10 and t is equal to 1 second. Therefore, what we have found is that if we kick a soccer ball at 20 meters per second at an angle of 30 degrees to the horizontal, that it takes 1 second for that soccer ball to reach its maximum height. Remember, this is the ideal situation. This is not a real world scenario. For example, there will be other forces in play like air resistance. This would cause our acceleration to change. Our a sub x and our a sub y will be slightly more complicated. In the MCAT, projectile motion questions always assume that the gravitational force is the only force acting on an object. One final type of motion that can come up on the MCAT is that of circular motion, the motion of an object in a circle. For example, you can consider a ball attached to a string and you swinging that string around above your head. Let's assume for a second that that object is moving at a constant velocity v. Naturally, the direction of this velocity vector v is changing all the time because the ball is moving in a circle. Therefore, the acceleration of the ball is 0, right? Well, not quite. Remember, velocity is a vector. Therefore, the velocity is changing not only if the magnitude of the velocity is changing, but also its direction. Since the direction of this velocity vector is changing, the velocity is therefore changing and there is therefore some sort of acceleration going on. This acceleration is known as the centripetal acceleration and it points towards the center of this circle, which would be where your arm is in this instance. This, if you like, is similar to the Earth rotating around the Sun. The Earth has a velocity vector v pointing in the direction of the circle, but the Earth is always accelerating towards the Sun, and therefore the acceleration vector points towards the Sun. As we shall also see in a future video, as there is an acceleration, there is also a force, and that force vector also points in the same direction as the acceleration vector. The velocity and acceleration of an object in circular motion are related as follows. A is equal to v squared over r. Again, as we shall see in a future video, force, mass, and acceleration are related by force is equal to mass multiplied by acceleration, and therefore the force is equal to mv squared over r, and that force is known as centripetal force. Please check the sample passages we have provided for you to see sample MCAT questions involving circular motion. As I'm going to discuss this relationship between force and acceleration in more detail in a future video, I will not go into any more detail about circular motion for now, but please see the sample passages we have provided for you to see sample MCAT questions about circular motion. To finish this video, let us now turn our attention towards some typical MCAT questions dealing with translational motion. The first question asks, which of the following is the correct definition for instantaneous velocity? Is it the change in distance per unit time, the change in displacement at a single instant in time, the change in speed per unit time, or the change in velocity at a single instant in time? Well, I'm immediately drawn to the word instantaneous. Remember, instantaneous means at a single instant in time. This means that only options B and D could be right. Also, we can immediately rule out option D because instantaneous velocity couldn't be a change in velocity. That doesn't really make any intuitive sense. Therefore, the answer must be B. Instantaneous velocity is equal to the change in displacement at a single instant in time. And remember also that instantaneous velocity is the same thing as instantaneous speed, but average velocity is different to average speed. This next question is testing our knowledge of vectors and scalars. Which of the following is not a type of vector? Acceleration, force, momentum, or mass? As I have not discussed what momentum is yet and whether it is a vector or a scalar, you should instead immediately be looking for the scalar rather than trying to rule out vectors. We know that acceleration is a vector. For example, the acceleration due to gravity points towards the center of the Earth. We know that a force is a vector. For example, a pushing force has a direction towards the object, and again, the gravitational force acts towards the center of the Earth. And we saw the centripetal force, which acts towards the center of the circle. Momentum we don't know about, but we do know that mass is a scalar. It is instead weight that is a vector. Weight is a type of force. Mass is just a number. For example, an object's mass is 30 kilograms. It is not 30 kilograms north, therefore mass is just a scalar. The third question is in relation to a dot product. We are told that the angle between two vectors A and B is 60 degrees. We are also told that the magnitude of one of these vectors, vector A, is 12, and that the dot product of the vectors is 30. The question is then asking us what is the magnitude of the second vector, vector B. Is it 5, 6, 18, or 24? Well, let's recall the definition of a dot product. If we have two vectors A and B, then A dot B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between them, the cosine of theta. Well, what do we know? Well, we are told in the question that the angle theta is 60 degrees, the magnitude of vector A is 12, and the dot product of vector A and B is 30. Subbing these into the equation, we get that 30 is equal to 12 multiplied by the magnitude of vector B multiplied by cosine of 60. Well, cosine of 60 is just a half, so therefore we get 30 is equal to 6 times the magnitude of B. And then doing some rearranging, we get that the magnitude of vector B is equal to 5, and the correct answer is therefore option A. The fourth question revolves around linear motion. We are told that a ball is thrown vertically upwards with an initial speed of 20 meters per second. We're then asked to find the total distance traveled after 5 seconds. Immediately, we must be careful here, okay? Remember, the Suvat equations do not have distance in them. The Suvat equations have displacement S in them, okay? Why is that important? Well, hypothetically, let's say in these 5 seconds, the ball goes upwards 10 meters before coming back down, say, another 3 meters. The total distance traveled in that case will be 10 plus 3, which is 13. But the total displacement will be 10 minus 3, which is 7, because that is the distance from its starting point to its end point. So the total distance is not the same thing as the total displacement. If in these 5 seconds the ball does not reach its maximum height, then the total distance would be equal to the total displacement, but we cannot assume that. We have to first check that. To check that, let's first check the time it takes for this ball to reach its maximum height. This is linear motion, so we only have one direction to worry about, but we do have to define which direction is positive. I will randomly choose up as positive, but again, you can check yourself. If you choose down as positive, you will get the same answer. As I am choosing up as positive, the initial velocity is therefore 20. The initial velocity is pointing upwards. What is the ball's final velocity? In other words, what is the ball's velocity at its maximum height? Well, let's think about the velocity vector. Initially, the velocity is 20 meters per second. As the ball is going up, the acceleration due to gravity is trying to push the ball back down. That is causing the velocity vector to decrease. At its maximum height, that is the point at which the velocity vector is 0. The velocity vector keeps getting smaller and smaller until at its maximum height, the velocity vector is 0. The velocity vector after that then points down as the ball goes back towards the ground. Therefore, at the maximum height, the final velocity is 0. As the question hasn't specified a value for the magnitude of the acceleration due to gravity, we shall take it as 10 meters per second squared. But remember, it is negative because I have to find the upwards direction as positive. Therefore, it is minus 10. Again, if I instead had to find the downwards direction as positive, we would have the acceleration as plus 10 meters per second squared. But remember, we have to be consistent. We would also have the initial velocity vector as being minus 20 meters per second, because remember, that is pointing upwards. And remember, we are looking for the time it takes for the ball to get to its maximum height. Therefore, we know u, the initial velocity, we know v, the final velocity, we know a, the acceleration, and we are looking for t, the time. We do not care about displacement. We want to use the Suvat equation, which does not have displacement in it. That is the equation v is equal to u plus at. Subbing in what we know, we get that v, which is 0, is equal to u, which is 20, plus a, which is plus minus 10, multiplied by t, which is what we're looking for. Solving this equation, we get 20 is equal to 10t, or t is equal to 2 seconds. What does this mean? This means that it takes the ball 2 seconds before it starts falling down again. Therefore, as we are asked for the total distance after 5 seconds, the total displacement is not equal to the total distance. How are we going to deal with this? The only thing we can do is split this question into 2 parts. First, we will calculate the ball's displacement from the ground to its maximum height, in other words, the displacement in the first 2 seconds. And then we will calculate the displacement of the ball in the last 3 seconds, when the ball is falling back down. For the first 2 seconds, well, we know everything except for displacement. We know u, we know v, we know a, and we know t. Therefore, we can use any equation of the 4 equations that has displacement in it. I will choose s is equal to ut plus a half at squared because it has s by its own on the left and I won't have to do any rearranging. So we have s is equal to ut, that's 20 multiplied by 2, plus a half at squared, that's a half multiplied by minus 10, remember acceleration is acting in the negative direction, multiplied by t squared, multiplied by 2 squared. Remember 2 we worked out earlier. Working that out, we then get s is equal to 20 meters. That means the displacement from its initial position to its maximum height is 20 meters. For the second part of the question, we need to work out the displacement in the last 3 seconds. What do we know about the last 3 seconds? Well, initially, the ball is at its maximum height. Therefore, initially, the ball has just gone from going up to going down, and therefore its initial velocity is 0. Again, the acceleration vector hasn't changed and the acceleration is minus 10. And the time is now the remaining time left over, which is 3 seconds. 5 seconds the total time, minus those 2 seconds going up. And we are looking for the displacement s. Here we know u, we know a, we know t, we know s. Therefore, we want the equation that does not have a v in it, which is the same equation as we just used. S is equal to ut plus a half at squared. Putting in our new numbers, we have s is equal to ut, u is 0, initial velocity is 0, t is 3, plus a half at squared, a half by minus 10 by time squared 3 squared. Working this out, we get s is equal to minus 45 meters. And hopefully that minus sign makes sense to you. Remember, we have to find upwards as positive. Because the ball is now going downwards, we should expect to get a minus answer for the displacement, which is what we do indeed get. Therefore, the ball has traveled 20 meters upwards in the first 2 seconds and 45 meters downwards in the final 3 seconds. Hence, in total, after 5 seconds, the total distance traveled by the ball is 20 plus 45, or 65 meters. If the question had instead asked us to find the total displacement, it would have been 20 minus 45, which would be minus 25. The ball would have been 25 meters below where it started. The final question deals with projectile motion, and it is a very general question. The question tells us that a projectile is thrown with an initial velocity u at an angle theta to the horizontal. It then asks us to find the maximum height of the particle in terms of the initial velocity and the angle. So this is the scenario we have. We have an object that is thrown at an initial velocity u, and we are asked to find the maximum height. Remember, because this is projectile motion in 2 dimensions, height is to do with displacement in the y direction, in other words, s sub y. We are being asked to find s sub y when the object is at its maximum height. As always in these questions, we have to define which directions are positive. Again, I will arbitrarily choose up and right to be positive, but again, choose different directions and see if you get the same answer you should. I'm now going to write down everything we know in this general question. Because our answer has the angle theta in it, we have to introduce that somehow into our Suvat equations. The only way to do that is by decomposing our initial velocity. The horizontal component of the initial velocity u sub x is equal to u cosine theta, and the vertical component u sub y is equal to u sine of theta. Remember, because this object is moving under the influence of gravity, we know that the acceleration in the x direction is 0 because gravity is pushing us towards the center of the earth, in other words, accelerating us vertically only. And we know that the acceleration in the y direction is simply the acceleration due to gravity, which is equal to g. I haven't put in 10 here because the answers have g in it, so we want to keep g there. And also there is a negative sign because I have to find the upwards direction as positive, and therefore acceleration is negative. Again, this is not enough information to answer the questions. We have 2 things we know in the x direction and 2 things in the y direction, the initial velocity and the acceleration. We need at least one more thing if we're going to use a Suvat equation, because each Suvat equation has 4 quantities in it. We need 3 quantities to find a 4th. Well, we haven't used the fact that the final position of the object is at the maximum height. What else is true about the object at the maximum height? Well, remember from a previous question that at the maximum height, the velocity is purely in the x direction. The object is only moving in the x direction at that instant. That means that since the maximum height is our final position, the final velocity in the y direction is also 0. Now we have enough information because we now know 3 things in the y direction. We have the initial velocity, we have the acceleration, and we have the final velocity. We know u, we know a, we know v, we are looking for s. We therefore do not care about time t. We therefore use the Suvat equation that does not have time t in it, which is v squared is equal to u squared plus 2as, which in the y direction becomes v sub y squared is equal to u sub y squared plus 2a sub y s sub y. Subbing in what we know, v sub y is 0, so we get 0 squared is equal to u sub y squared. Remember, u sub y is u sine theta, so we get u squared sine squared theta plus 2a sub y. A sub y is minus g, multiplied by s sub y, which we are looking for. If we then rearrange this equation, we get our answer. We get that s sub y is equal to u squared sine squared theta over 2 multiplied by g, which is option A. To finish this video off, let us recap what we learned. To begin, I introduced the idea of units and why they are important in physics. I emphasized that in the MCAT, you typically find metric rather than imperial units, and then discussed each of the 7 base units. Then I talked about the differences between scalars and vectors. Scalars have magnitude only, whereas vectors also have direction. I also mentioned various examples of each. For example, speed is an example of a scalar, but velocity is an example of a vector. Then I moved on to describe how we add and subtract vectors, and the different methods there are to doing it. For example, the tip-to-tail method, which is a good way of visualizing the addition of vectors, before moving on to decomposing vectors and adding them in that way. I then described how multiplying a vector by a scalar changes the magnitude of the vector only and may also cause the vector to flip. Multiplying a vector by a vector can be done in 2 ways depending on whether we expect a scalar or a vector to be returned. If it's a scalar, we use the dot product, and if it's a vector, we use the cross product, using the right-hand rule to find the direction of that resultant vector. I then moved on to talk about various types of vectors. For example, displacement, which is the vector equivalent of distance, but does not care about the path taken. It is path independent. Remember, if you travel along a messy curve, the distance is equal to the length of that messy curve, but the displacement is simply the distance between your starting and end points. Similarly, velocity is the vector equivalent of speed and is equal to the change in displacement with respect to time. I also discussed how instantaneous speed and velocity are the same, but average speed and average velocity are not the same because they care about whether you're using displacement or distance. Then I moved on to the idea of a force, which is something that causes an object to accelerate. Examples of forces that I listed were gravity and electrostatic. But another force that I have not talked about yet is friction, and that I will discuss in a later video. I then discussed the important differences between mass and weight and how they are often confused in the real world. As a final example of a vector, I discussed acceleration, which is the change in velocity per unit time. Finishing the discussion on vectors by introducing the concept of instantaneous and average acceleration. Obviously, you should say acceleration there and not velocity. I then used these concepts of vectors in both linear and projectile motion to describe the motion of a particle undergoing acceleration. I then wrap things up with translational motion by introducing one final motion type that you need to know for the MCAT, which is circular motion. Hopefully this video has been helpful to you in understanding ideas around translational motion. Again, please practice with the sample passages we have provided for you until you feel confident in answering questions on translational motion in the MCAT. Thank you for listening, and I'll see you guys in the next video.